Hello there, I am Sonal Kumar. This poster presents our paper titled GraPix, Exploring Graph Modularity for Pixel Clustering. Self-supervised vision transformer learns high-quality patch embeddings with the self-attention mechanism. Patch embeddings play a crucial role in many unsupervised downstream tasks like object localization, detection, and segmentation. The existing approach for similar tasks creates a similarity-based patch affinity graph with patch embeddings and takes greedy or learning approach. For example, the token cut utilizes normalized cut with patch affinity graph to separate foreground and background patches. We observe that patch embeddings from the same visual group are highly correlated. One of the recent methods for unsupervised DSS, called STIGO, utilizes the feature correspondence between nearest neighbor images with contrastive loss for unsupervised training. The takeaway is that the shared semantic information can provide informative supervision for downstream training. Similarly, another method, that is, utilizes a graph clustering algorithm called Louvain with a patch affinity graph to identify different objects in a scene. Here, the Louvain algorithm performs hierarchical clustering by maximizing the modularity of a graph. Modularity is an important property of a graph, which reflects the strength of the existing graph partitions. Here, the takeaway is that the graph partitions with maximum modularity align with the different visual groups, image segments, present in scene-centric image. The true potential of the patch affinity graph is yet to be harnessed for the end-to-end dense semantic segmentation task. We argue that maximizing the modularity can improve the quality of graph partitions and the corresponding image segments. Hence, we propose an end-to-end learning approach, called GraPix, with a pre-trained self-supervised VIT for dense semantic segmentation. GraPix utilizes the modularity property of the similarity-based patch affinity graph to train an unsupervised semantic segmentation model. The major components of the GraPix are 1. Self-supervised training setup, 2. Trainable cluster centroids, and 3. Unsupervised segmentation loss. The self-supervised training setup consists of a pre-trained self-supervised VIT with a projection head to extract the patch embeddings. Next, the patch embeddings are processed to construct a similarity-based patch affinity graph. Also, the patch embeddings are assigned cluster labels based on their distance from the centroid embeddings to form the graph partitions. Finally, the unsupervised segmentation loss utilizes a patch affinity graph along with assigned patchwise cluster labels. It maximizes the graph modularity and minimizes the distance of patch embeddings with corresponding centroids. As shown in the figure, the unsupervised segmentation loss is a combination of clustering, modularity, and orthogonal loss. The clustering loss reduces the distance between points and corresponding cluster. Next, the modularity loss increases the intra-class connections and decreases the inter-class connections. Finally, the orthogonal loss ensures that the patch embeddings from two different visual groups are orthogonal in patch embedding space. In this way, the GraPix jointly optimizes the clustering objective in patch embedding space and node attribute space to learn discriminative cluster centroids. We also propose two additional unsupervised training methods, KNN and self-label training. They leverage the learned centroid embedding with GraPix to generate class-level quality supervision from the dataset for fine-tuning the framework. The qualitative and quantitative results show that the GraPix outperforms the state-of-the-art methods on the SUIN dataset and achieves the second-best performance on the Cityscapes dataset. However, unsupervised learning methods suffer from an overclustering problem, which can be noticed in visual results. We have also performed an ablation study to justify module choices and hyperparameters selection. Thank you for your attention. Let us know if you have any questions. Please scan the respective QR code to connect on LinkedIn and access the GitHub repository.